recording now, and I think you will need to interrupt me with voice if there's some questions in the chat, because if I share the screen now, maybe will be harder to see. So today the subject will be the Solovay-Kitaev algorithm, and here's the archive number. So quant physics 0505030 by Dawson and Nielsen. Okay, that's the standard traditional reference for this Solovay-Kitaev algorithm. Zooming in a bit more. So still the number here, title and paper. Okay, another thing that I want to show is maybe to show more or less where we are headed. So if we just scroll through, this is maybe a bit too small. We will have a definition that is important. Then I would like to skip through most of the text, but papers by Nielsen are extremely well written, so usually it's a bad idea to skip. Then we have the actual theorem and some algorithms that we want to maybe see. And then there's the technical bits, for example, approximating the commutator, and a more, let's say, generalized or refined version of the theorem here, and a little bit of linear algebra theory, which is quite interesting, but probably we won't come to it. Okay, and then we are more or less at the conclusion. So that's the structure of the paper. We have 14 pages, so we will not be able to do everything. And before reading the paper, it's also useful to have a look at Wikipedia. So let's see, Wikipedia. Okay. So the article I was looking it up today, it's actually giving some intuition about what's going on. And maybe I should say a little bit more about the setting before I come to this on Wikipedia. So let me go back to the notes. So maybe I will have some space here and I will write here. So let's say I have a gate set, G1 until GK. And I want to call it, then it's universal. If I can consider any unitary V in the unitary group on maybe D dimensions, then I can find a sequence of gates. So GI1 ... GI capital N, such that I will approximate my unitary V. Okay. And if I'm able to do that, I would call this a circuit because I have a specific number of types of gates. And I compiled this particular target unitary with those gates. Okay. So that would be compiling some algorithm, compiling some circuits, doing something. Okay. So you could view a quantum computer as a machine that takes some fixed reference state psi and produces any state phi out of that state. Okay, those are essentially quantum algorithms. And then this state here will have some properties that encode the computational task that we are interested in. Okay, so actually if phi is my target, then I can approximate phi using GI1 until GIN. So that would be the universality. Now the question is, for example, what happens if I have a different gate set, G tilde until GK prime tilde, okay? And the question is whether this is equivalent. Okay. And the Solovay-Kitaev algorithm answers that question. Okay. And actually the question is yes. And basically G1 is a unitary matrix. Again, maybe on some dimension D. And what we will have is that G1 tilde, we can approximate with our initial gate set G1 until GK. Whoops, not like this. GI1 until I sum n tilde. And this n is a function of what operator we want to approximate, of course. Okay, so sometimes it will be short, sometimes it will be long. Okay, so first application of Solovay-Kitaev that you will find is that basically it shows that universal gate sets can be mapped into each other typically. Okay, so what is one example of that? Basically the first part of the paper will make it precise what we mean by a gate set. So they call it an instruction set and so on. But basically here in this notation we would have G and G prime, two gate sets. Okay, and basically if we come to the theorem later, it will have some epsilons and so on. Okay, and it's explaining that it's possible to map one gate set to another. Okay, so we want to come to this theorem in a moment. So this is where we will stop later, but there will be also an epsilon and so on. So the things that I discussed, that we want to have an epsilon approximation of some target unitary, then that's it. Okay. If we look at the abstract, so we are in this archive paper here, and so let's look at the abstract. Maybe I will not go line by line through the paper, but okay. I confirm that this is pedagogical. It's really a nice paper. And it actually focuses on the proof of the Solovay-Kitaev theorem. And that's why I want to go to Wikipedia, because Wikipedia focuses on the idea and I don't want to focus on the proof. And it's an efficient classical algorithm. Okay, it's for compiling an arbitrary single qubit gate into sequence of gates from a fixed and finite gate set. Okay, so what does it mean? Later in the next sentence, they say, okay, the algorithm can be used, for example, to compile Shor's algorithm. And Shor's algorithm will use controlled rotations or controlled unitaries, and then Fourier transform where we need angles. Okay. And if we want to make it a fault-tolerant algorithm, then for typical codes, you would only have this gate set. Okay. So basically, what's going on here in the background is that if we have a surface code and we have some measurements on the qubits, so sometimes we will measure here and sometimes we will measure here. Then we will protect the encoded state, and applying a single logical qubit operation means that we will be applying an operation on the entire system, so to speak. Those are transversal gates, for example. Okay, so a fault-tolerant gate is actually a big physical operation, and those operations tend to be quite expensive because we are protecting our system, but the price to pay is that you need to apply stuff to the entire system. And when you work with this logically encoded qubit, then it's not so easy to get something which is simple for a single qubit. So for example, a phase gate. Okay, this is not so easy to do on a surface code. And instead is what I highlight here. Instead, you will be using the Hadamard operations. Single qubit Pauli flips you can do on the logical space. So I will put a bar. So for the logical qubit, you can do this still. Controlled knots are still okay. But pi/8 gates is something that is called magic state injection, and magic state distillation is needed to have those gates in the surface code in a good way. So that becomes more complicated. But basically, you can think of this gate as R phi pi8. Okay, so it's a rotation by this pi/8 gate in the angle there, and that would be called the T gate. Okay, and T gate plus C naught and single qubit rotations gives us universality. And what this T gate actually does in the surface code is that basically, if I have my logical qubit, I could, for example, swap the qubit, the state of the qubit, so 0 to 1, or I could use this logical Hadamard to go to the logically encoded plus state. But just with those operations, they are Clifford operations, I can only swap here on the axis of the block sphere, but I cannot go, for example, here so easily. Okay, and this is what the T gate does for us. It gives us this angle. And then when we have the block sphere, okay, let me show it again. Like this, maybe. No, not the best drawing ever. But basically, if I rotate here, then I'm here. And then if I rotate around the z-axis, then I will go here and so on. So then maybe I want to swap here and so on. So then you start doing this, and you can slowly keep kicking it around and rotating it around. Okay. So maybe kick it here, maybe kick it here. And then at some point you will get again a Z rotation, but not by 1/2 of the rotation, which is the Hadamard, and not flipping it, which is the X operation, but maybe to some arbitrary angle alpha. Okay. And achieving this in the fault-tolerant way on a surface code would involve those T gates. T gates meaning this. Okay. So that's why they are saying this, that it's not so obvious how to get this, but what they are showing there, or that's implied, this is just standard Nielsen-Schwank stuff. For Shor's algorithm, we need those gates. And then if I want to have R of pi/2k, which is my angle, then I need to use my gates G1 until Gn. And those gates Gk will be in the logical space X, Y, Z. It will be the logical Hadamard, and it will be the logical T gate. Okay, and out of that we can get those small angles. It's quite a complicated procedure. So doing something which is simple for a single qubit. For a single qubit, if I want to rotate here, I can choose an angle and have some generators, some magnetic fields, B vector and then sigma vector. And that will be rotating my block sphere around. Okay, so this is just the Euler decomposition. Maybe some choice of those rotations we can pick. Okay.
So is there a reason that we work with the set of unitaries instead of the set of generators?
Sorry, can you say it again?
Is there a reason that we work with the set of unitaries instead of the set of generators? Like, we essentially, like, at the end of the day, we control them by like applying some pulses for some time.
So yeah, exactly. So in single qubit rotations, it's easy to have a small angle because you control the angle by the time. Okay. But if you're encoded, it's difficult to get those small angles because the unitary is actually acting on an entangled set of states where all qubits are in some funky way correlated with other qubits in a special way, which are those special error correcting states. Yeah. And applying a rotation in the logical subspace is difficult because it becomes so if I have my logical state 0 and I want to get 0 plus I phi 1, then this becomes difficult because achieving the superposition means that the global system comes into superposition, and for this we are using T-gates. Okay, but the T-gate in one go gives me a small angle, which is pi over 4, I believe. Like on the block sphere, it will be somewhere here. And then you can do some operations, go, and try to be maybe at pi over 8. Okay, and so on and so on. So I think in this notation, there would be 2 I phi or something like this.
So like you can make T-gate by doing some things, right? Like turning on and off some pulses or something. Is it like that difficult to make, let's say, pi over 16 gates? This continuous family.
In the surface code, you will always do some pulses, but it's not so much. So the procedure is called magic state injection. So if I have my working space here and I have maybe 0 to tensor power n encoded in my surface code patch here, then the size of like a single logical qubit here is some size. Okay. And basically we will have some chunks. Let me just sketch it out. Let's say this is qubit 1, this is qubit 2, 3, and 4. Let's say it's just a simple picture like this. Then I can have one more qubit, which will be giving me those T states. And basically, if I want to achieve this, I will be doing pulses on the individual physical qubits, which are somewhere here. Okay. And this should become in the T state here, which will be 0 plus I pi over 4, 1, I think. I'm not so sure about this pi over 4, but I think that that's the angle. Pi over half would be essentially the plus state, right?
So the problem is that magic state with smaller angles are more difficult to generate? Or?
Yeah, so actually the problem is Nick Fazio was explaining it to me the other day. The problem is not so much getting it here, but getting it deterministically and then correcting it. So basically, you could try to inject it there, but first of all, making it fault tolerant is difficult, and second of all, when you are injecting the gate using that state, which is this magic state injection, which is then doing the T gates. So I can use this state to perform the T gate, for example, on this qubit. Then to correct it to make it deterministic, because it's depending on some stochastic measurement outcome. You need further Clifford operations to correct it. But if you would be injecting pi over 16, then you will need T gates, those kind of T gates to make the corrections. So
I see.
So basically, there is something called Clifford hierarchy. And if I didn't mistake the notation and pi4 is correct, I never know. But if this is the basic T-gate as in the Solovay-Kitaev paper, then what they are showing in that paper is that using those Hadamards and X operations and so on, you can get exactly this T-gate operation here. Okay, as a unitary. So we swap a state to make an operation. If I would be using a larger angle, pi/8 or pi/16, I would have to go to higher orders of the Clifford hierarchy to correct them. And to get those higher orders, you would need T-gates at some point. So,
Right, so T-gate is like a particularly nice.
it's nice because it magically closes. That's part of the magic of magic states.
Right.
So basically, the magic of T-gates is that you can make the injection deterministic, even if the measurement outcome doesn't prepare the T operation, then it will be something which has some Clifford operations. And then, so let's say you wanted to apply T, but sometimes the measurement will be such that this will be T together with some Clifford operations. So you add the inverse Clifford operation here, which consists of logical X, Z, Y, and Hadamard. If you want to inject other angles, then you will need T-gates to correct. That's one point. Okay. Okay. So now, after reading this paper and implementing this, you could, for example, try to understand that if I have some operation O together with my T-gate logically, how to compile using T-gate and single-qubit logical gates, how to compile the inverse of that operation. That's one idea. So this Solovay-Kitaev algorithm allows you to, how to say, give the answers of how to do it, how to, for example, find a specific operation that you want to correct. Yeah. And it allows you to do this out of any universal gate set. And this gate set here is particularly well suited for surface codes. Okay. And that's good because that gives you fault tolerance. So Nielsen always was writing very good papers. The textbook is also great, and that's a very sound logic. This is giving one example, which is really the key example. I don't know if you can come up with like many better examples. Other examples would be just like that there's many instances where you might want to compile something, for example, those corrections with higher order Clifford hierarchy. You could algorithmically try to do it. Okay. So the algorithm runs in some time, and the time is in terms of an epsilon, which means how well do I want to approximate my epsilon, and the runtime. The running time is n. So to speak, how many of those gate set operations do I need to sequentially apply to get my operation? Okay. So that's one thing. Okay. And it produces an output, a sequence of some length of quantum gates. So it's again in 1/epsilon and so on. Okay. So if epsilon is small, epsilon to 1/epsilon is bigger. Yeah. So that's why it's maybe giving us the length. And it's guaranteed to approximate the desired quantum gate with accuracy epsilon. And we had it earlier in the tutorials. Nielsen actually starts here with that somewhere here. The notion of approximation is approximation in operator norm. So I did a good job. I said that's the fundamental thing. And we were also talking about this to say like the distance between the unitary and my sequence of gates that I have is the norm of the difference, which is actually the largest difference of applying those gates to the same state, and so I can search for a state that basically will witness the difference in those operations in the most prominent way. That's kind of the meaning of operator norm. So there's a reading of this in terms of singular values, as we were saying, but this is more physical, saying that there might be a state where I apply my unitary, I get something, and I get another state, and those states are maximally different. But this algorithm will say the differences will be small. This is our target epsilon. Okay, so that's already in the abstract here. That's this accuracy epsilon here. Okay, last sentence, the desired quantum gate. We also explain how to multi-qubit gates and to gates from SU of D. So SU of 2 are single qubit gates. And that's important because if I have this universal single qubit gate set, then I have this kind of discrete operation, the T gate. And if I want to have small angles, then basically I want to have those SU2 operations. So the meaning of SU2, if you see it in the paper, it's not a boring block sphere because it might be the logical block sphere. That's a more advanced reading of it, and that makes it non-trivial. I mean, single qubit gates would be also non-trivial, but for the physical single qubit gate, so if I have a transmon in the lab, then I can get those angles for free. I have basically a continuous gate set because I have a continuous way of varying the pulse lengths, okay? So my gate set on physical qubits is in principle continuous. Now, in the logical space, we want to discretize it because there's a certain way of working with error correcting codes where where basically a logical operation, it involves all the qubits in the system, essentially, or basically many physical qubits, and basically it's not easy to make arbitrary operations, and those operations are at least reasonably feasible. That's why we are talking about those Clifford plus T gates operations for surface codes. Okay, I think that's enough scribbles, but multi-qubit gates might mean that we have SU C2 tensor C2. So basically, for example, we would like to have some evolution step e2 minus IT x tensor x. And then you might want to ask how to use C0 plus XY Z Hadamard and T gate, for example. The logical ones. Okay. Logical. So how to use this and get that. So that's what they mean by multi-qubit gates. And gates from SUD is the same thing because C to power 4 is isomorphic to C2 tensor 2. Okay, so that's a similar thing. Okay, so sorry about all the scribbles, but we already understood whatever it says here about the Shor's algorithm. We more or less understood that. Okay, so if you're happy with what I said, then we can continue. But let's see. This is again very good writing by the authors there. The purpose of the present paper is to present a proof in form of a concrete algorithm. And it's not the point of presenting the algorithm, but what does it do, which can be used to approximate a desired unitary U. Okay, so this is what I was trying to say here. We say it in one line. And then it's also connecting with the mindset of how to work with this, so you can try to read it later and see whether you agree with those thoughts by Knut and so on. So we see here compilation. Let's see what we have. The basic goal of the Solovay-Kitaev algorithm is to take an arbitrary U. So that's also the limitation of it. So if you give me 1000 qubits, I cannot use the Solovay-Kitaev algorithm to compile any 1000 qubit unitary because I will need to work with that unitary in the algorithm. Okay. So one thing that we need to watch out is dimension of U. Are there some limitations on whether we can work with that? And if it becomes unhandy to be working with the algorithm that we will see below, then it means that we will need other ways of compiling larger unitaries. And those are basically quantum circuits. This is basically how people build quantum algorithms on many qubits. Okay, for smaller amounts of qubits, like 2 qubits, 1 qubit or 2 qubits and so on, you would use this algorithm. Okay, because it becomes efficient to work with this. And then they will tell us now what's the point of this. The point is to use a sequence of gates drawn from a finite set, drawn or actually belonging to that finite set of gates G. Okay, and that basically gives us this practical prescription, because we say do GI1, GI2, and that gives me the approximation to the algorithm. Okay, that's the mindset here. This is how we turn those kind of gates from the gate set into arbitrary unitaries. Okay, so why we will call this compilation? Okay, so we will have a language, and then we just write this in the human language. They want to say that the human language for fault-tolerant codes would be Clifford's and T-gate. Okay, it's actually how people in quantum information talk about algorithm at all, a lot. It will be this kind of language. And then to the native machine language, which are the pulses and so on. And basically, the gate set is equivalent to knowing how to do the pulses. So if you say that's my gate set, it means in the experiment I know the pulses. Okay. But if I know the pulses for those gates, I might not know how to put the pulses together to get some unitary U here. Okay. So I would need to make a sequence of my known pulses to approximate that, and that's what we mean by quantum compiling. Yeah, so we will have a set of quantum gates from the instruction set, gate set, and the process of finding good approximation is compilation. And good approximation means up to some epsilon. Okay, but because quantum stuff is quite continuous, and Chongrak, you were actually asking about this, it's like can do maybe any pulse directly on the physical qubit. So then it becomes a bit blurry what's going on. I think this fault-tolerant stuff, which is related to something called transversal gates, is actually motivating like what is the basic gate sets that is the right language of talking about fault-tolerant quantum algorithms. Okay, so they said maybe, you know, maybe it should not be taken so seriously, but this was in 2005, and 15 years later we seriously talk about compiling, so it's actually quite nice. But I think like because of this sentence, they don't call it the Solovay-Kitaev compiling, but the algorithm. Okay, so the definition of the gate set is quite interesting. So for a d-dimensional qubit, or you have a qubit, which is a 4-dimensional system, which is equivalent to 2 qubits. And then the instruction set is a finite set of gates. And all those gates are unitary. They are actually special unitary, but that's fine. and they actually say it. This is pedagogical. Okay, so the gates are unitary and have determinant 1. That's what special unitary means, and that's important because of exponentiation. So John Gregory mentioned the Hamiltonians, and why don't we speak about generators and unitaries? We bring into focus because when we operate on the quantum computer, we will be changing the state of this quantum Turing machine. Our operations will be unitary operations. So if you have a classical Turing machine with a tape, the operations would be something. In the quantum computer, it will be applying the unitaries and not so much switching on the Hamiltonian. I think this is a bit of an ontology question, but the generators are not so important here in this case. Another point that they really highlight here is that there are inverse operations, G dagger. Inverse because unitary, so inverse is G dagger, and it's also in the gate set. What does it mean? It means that if I have e to I phi k, some generator, then I also need to have e to minus I phi k. So I can swap the angles. And why this will be important is because of the group commutator that I was showing before. So I will go here. And this you should recognize as the group commutator. And to get the group commutator involving I phi and then maybe some unitary W, I need also the inverse. So if this is my gate Gi, and this will be some Gi prime gate. Okay. Okay. Yeah. So to avoid inverting this, I say I need the inverse already in the gate set, so I just keep applying this. Okay. That's why number 2. Number 1 is physicality of the operations. Number 2 is a condition. And then G is a universal gate set for all of those operations that we can possibly do. If the group generator by G is dense in SUD, and dense means that basically for any epsilon, there exists a sequence of of operations G, such that if we concatenate them, we will have any unitary minus some circuit Cn is smaller than epsilon for n sufficiently large. Okay, that's being dense. It's the same as saying that if I have a continuous interval 0 and 1, I have rational numbers and they get more dense and more dense. So at some point I can approximate 1 over pi. I don't know, somewhere between 0 and 1, right? So in the same way, if we have our block sphere and we have arbitrary rotations u, somewhere here we can approximate this continuous range of angles arbitrarily well. And it's very similar in the fault-tolerant case to actually the rational approximations to some real numbers. So here we have, oh, sorry about this. So here we have Q rational numbers converge. So rational numbers P and Q, integers like, I don't know, 1 over 3 and so on. And here we will have full angles, so X, Y, Z, and this pi over 8 rotation. And this pi over 8 rotation will be adding a new factor, so we can always get maybe P to 2 power K rotations. And once we have this, we have a binary approximation to some fraction. So it's very, very similar actually to this dense is again, like it's not by accident written here. It's a really good paper here. This means that given any quantum gate U and any accuracy epsilon, there exists a product S, I wrote, I think C, of gates which an epsilon approximation to U. Okay. And because I can keep making this epsilon smaller and smaller, I can get convergence to any unitary. Okay. So any questions to this definition? It's making more precise what it means that I have a universal gate set and what universality means. Universality means approximation up to any epsilon. And universal gate set means a set of operations that achieves that. Okay. So some notation here that I think I will skip. So I'm scrolling down. The elementary operations we saw in the previous session. So I think we are fine there. Okay. So operations 1 and 3 is easy to understand. It's more or less standard. Less clear is the reason for part 2. And again, that's why I really like this paper. Why I keep saying it's well written. Is because they explicitly say in a dedicated paragraph that there's no a priori reason. Okay. So now I stop screen sharing and I show you what happened 10 years later. So, okay, we have on the archive the paper that we are studying now. And later, actually 2017, Adam and Maris, they wrote this paper here. And as I understand, that's kind of the starting point. And maybe this this paper is kind of bringing that question, this line of reasoning to completeness. So an inverse free Solovay-Kitaev algorithm, I'm not familiar with this paper, but this is the bridging tutorial, so we can have a look in a second. But if I see this and I know the classic paper by Dawson and Nielsen, I'm like, this is removing this this point number 2. And I think why everybody was aware of this is because they really explicitly pointed it out here as an open problem. So I was aware of this and so on because you read the paper and it's really explained to you that there's no a priori reason, maybe you can remove it. So I think in this paper they worked it out. So let's see. Okay, so if you have any gate set which generates SUD, it doesn't need to be complete under inverses. Then you still have any approximation of the unitary, and the length of the sequence is again scaling like this, epsilon to -1. Let's see in the Solovay-Kitaev algorithm. So basically they are saying you are losing essentially nothing. So a sequence of quantum gates, so that's the length of the circuit, and the scaling here is log to some rational power, so it's bounded by log to power 4. 1 over epsilon. So the classic paper was log to power 4, and here they say log to some power n. Okay.
So I have a quick question, maybe.
Yeah.
So where does this epsilon error come from?
The epsilon error means let's have a look. The epsilon error is your threshold to say when are you satisfied with the implementation of your unitary. So for example,
this is independent of like the physical error sources, right? Because we are only dealing with the
no, this is more the requirement of saying if I did this operation up to some epsilon, then I'm satisfied. So for example, in the surface code, if we want to rotate to some angle, we could make some continuous fraction approximation to that angle, and then keep applying those rotations, right? So basically, to get any angle, you need to decompose it to get the T gates, right? So basically, you could say, I want to approximate my continuous numbers by rational numbers by the quotient of some digits. some floating precision. So you could think of this as the equivalent of the double or floating point precision in regular numerics, right? So if I work in NumPy, I have approximations of real numbers up to 10 to minus 14. That's my standard precision of matrix multiplications and so on, right? So that's kind of the floating point precision, and the epsilon is here.
Yeah, okay.
Yeah.
So this purely comes from the numerical approximation. Like it's independent of the physical error sources.
It's physical errors are what we have in the system, and this is more the requirement that we want the engineers to meet, right? So, and then it's also natural that if you want to have a better precision of approximating all those target unitaries, then maybe you need to compile longer. And for floating point precision, it's kind of similar because you're approximating by longer bit strings the numbers, right? So you will make more multiplications, so the operations will be also longer classically.
Yeah, I mean, I understand that, but this is independent of, like, say, the fidelity of G1, G2, and so on.
Yeah, so it is independent, but in the end, you set it yourself and also in comparison to your system, right? So this epsilon doesn't need to be fixed in stone. Sometimes maybe it's okay for you to compile something a little bit more noisy, and sometimes maybe you want to be very precise. Because maybe this is just a modular operation, a primitive operation to compile a larger circuit. And maybe in the larger circuit, it doesn't influence so much and so on. If I kind of do it a bit more sloppy here, and then maybe sometimes more precise and shuttle it around. So basically this epsilon is for us. If we can do something smart with it, we can change it. If not, just make it 10 to minus 14 if you can, and then you have some epsilon, yeah? And the point is that if my epsilon is 10 to minus 3 for maybe quantum hardware, then the length of the operations would be 10 to power 3. So 1000 operations to compile one gate with precision 10 to power minus 3, for example. That would be the idea. Okay, so 1 over epsilon is translated to the length. It basically inflates how long our sequences will be. But for more mathematicians, there's no difference between E minus 1 and E minus 1 minus 4 or something like this. It's a polynomial inflation of it, but it's not exponential, so everybody's happy.
Yeah, okay.
So we are saying like there's a small trade-off. This poly, seeing this poly here, you should think there's a small trade-off that I don't need to change it. And okay, so the exponent that we say is 862 compared to an exponent of roughly 397. And that's the exponent we see here. Okay, so we really connect to the classic paper. Okay, yeah.
So what I don't understand is that this universal set is already universal even without the inverse, right?
Yeah.
Then I believe like you can generate the compile the inverses with constant depth.
Yeah, but maybe compiling those inverses could be costly, and that's the thing that they are answering here.
You mean they might not be constant depths? Or...
It might be very costly to maybe compile them. You would need to know. Okay. It's not entirely
because the universal set is just like general for now.
Universal means existence, and it's a stronger reference to say efficient existence. Okay, and efficient means it's polynomial in some relevant parameter. Okay, so
yeah, because like the typical example we have, the Clifford and T. I guess there it should be easy, like fairly easy to make inverses.
Yeah. So the T gate you can actually probably inject to get the inverse of the T-gate as well.
Yeah.
So
And
I
quick
think
folds
what-
are just like quick folds.
Yeah. So actually, without looking up the paper and fully trusting those authors here, you see, okay, the inverse of the T-gate is also fine in the surface code setting, because they explicitly wanted to have those inverses here. Okay, so the T inverse is also possible to get. Yeah,
Okay.
and the first paper actually, sorry, maybe actually Michał had the first paper on this. So Michał Oszmaniec, Ignacy Sawicki, and I think Michał Porodecki, yeah. They were studying those epsilon nets, and they say here, okay, they had this inverse free thing here, and that was actually a lemma, I think, in the algebras that we are proving there. Let me see if I can find it. So anyway, the progress was coming from other fields of mathematics until this was ripe for it. And okay, so we are actually crediting them with information theoretic of SK without inverses, short sequences of gates that approximate an unitary. Okay. And what they say they do now is they repeat the Dawson paper, to Dawson-Nielsen, to algorithmically define those sequences, because the existence of a short sequence is kind of a question of finding like a good epsilon net and converging within the epsilon net. Not something I'm able to discuss today, but you see again some distances and so on. And let me see if I can find. I think maybe I know where the key result is. It's really it's really not so easy to read those papers. It's tough stuff. So this expander might be already the. But I think in this paper there's a lemma on the algebras. No, sorry, I cannot find it now. Okay, but you have the link here. It's cited in the other papers as well. Yeah, no, I cannot find it now. But basically, if it's not algorithmic, it's more the existence. And maybe I will sketch it still, and just to complete that discussion. This is also relevant. If you read the paper, I think they don't focus so much on those epsilon nets. So basically, let me say, if I have a circle or a sphere, then there's a problem of saying how many patches can I do such that any unitary. So I consider points on my sphere, and those points should have some radius r here, such that I make those patches. So you can think of a football. A football is a little bit like an epsilon net, because if I look at some patches on the football, if I look at the centers, then the central points are maybe up to some large epsilon on a football, but you can make it smaller and smaller. So that becomes a more continuous ball, right? And then those points here are more or less gates. So if you find good epsilon nets, you get some compiling and so on. Why is this not algorithmic? It's not algorithmic because it's a random walk probably on the epsilon net. You saw some random walk T design stuff and so on. So basically you start here, you start walking around, and you try to minimize the distance to some target operation, and you see that this random walk will converge onto any point. So if I have maybe here some point, but I want to get here, then I need to walk around on those points and find that point. I need to find this. And the question is when, for example, a random point will hit that point, how long do I need to do it? And then you say there exists such a sequence. Okay, it's an existence and not efficient. So that's what was solved in the paper. Okay, let's have a look still. I'm not really explaining the algorithm, but I think if you get the ideas, then you can just read the paper and get the calculations, because this is like Nielsen one. It's just if Nielsen says pedagogical, it will be pedagogical. Okay. So let's try to see what will be the really key insight. And the key insight historically is that that you had Solovay and Kitaev. They announced that theorem, and then later Dawson and Nielsen are also cited here on Wikipedia that they kind of showed the importance for the field. Okay, so the statement we saw, the statement here we also saw. Okay, so we go. So so there's one thing where I will need to write, but the point is of giving increasingly good approximations to you. And there's a little bit of convoluted discussion that I want to skip what that means here, but I want to show you the relevant formula. So let's say I have already two operations, V and W, and they are in this SU2 here. And those V and W are away from the identity by some delta. Okay, and if I have some approximations to those operations, okay, then I can look at the group commutator, and the difference of group commutators will be actually smaller. Okay, so let me write down those formulas. Page, and I need to share the screen. So if I get it right, we are almost done with the discussion that I wanted to show, and then we can just say what it does. So we will need to understand why it's enough to look at something like this, delta 1, V minus identity delta 2. But what they are explaining, and then W tilde is, I think we need delta. Yeah. And V minus some approximation to V is also delta. And now let's look at V minus 1, V minus 1 minus V tilde as well, W minus 1 tilde, V tilde minus 1, and this is smaller than O of delta 1 delta 2. Okay, first thing, why is this a good thing? Let's say delta 1 is equals to delta 2 is 0.1. So basically out of an error, let's say 0.1, I will get an error 0.1 squared, which is 0.01. Ooh, it's looking good, right? So now let's say I will have two new approximations, which are 0.01. Okay. So out of that, I will create delta 1 times delta 2. I will get 0.01 squared, which is, okay, I'm getting some digits. I think like this, right? So 10 to minus 1 becomes 10 to minus 2 becomes 10 to minus 4. And we are getting at some point 10 to minus 2 to power n in those approximations. So basically it's the approximations converge very fast. Yeah. And why is this good? we were talking about the approximation epsilon. So I want to have a sequence of gates such that I approximate a target unitary that my client wants up to epsilon. And we were saying we can achieve this with log 1 epsilon, and this is related to that, right? So this error is shrinking, it's collapsing exponentially fast. That's why we have this logarithmic speed of doing this operation, okay? That's one thing that is important. Now, what's the idea with this? So I explained why is it good that we will be getting that approximation, and this you have on Wikipedia. It's probably just a technicality to just go through the steps. Okay, so once I have this group commutator we were discussing in previous sessions, we understand more or less what's going on with the group commutator, great. But now what's going on with this? What's going on with this? So why in the world are you looking at how far away is it from the identity? And this has something to do with Lie groups. So if I have the identity element on my Lie group, then my Lie algebra is actually telling me in which direction to go. So it's something related to tangent spaces. I will not say more. But let's look at this condition. I want W identity and like this. Okay. And I want this to be smaller than delta 1. So what will be the meaning of this? And that's what I was skipping before. But let's say I have already some approximation to U minus the first sequence of gates is delta 0. Okay. Then I can consider U and invert the gate set, the sequence of gates with a dagger. And then I need to consider the identity. I get a delta 0. Why? This is something we can prove because U minus okay, we were seeing something like this. This is unitary invariance of the operator, no? So if I have U minus S, this is equals to setting, oh, this is maybe a bad notation, some U bar, any unitary operations. I can for free put in any unitary operation on outside. So I will put identity on the left and minus S, and I will put the unitary operation S dagger here. This is equal because of the unitary invariance. So if I multiply it out, I will have identity US, okay, simple stuff, minus identity S dagger is the identity. So I get U as dagger, sorry, here as dagger, minus identity, okay? Which means if I'm searching for approximations to my target unitary, I could also check what is such an object doing, and we will be calling this more or less W, okay? So basically the brilliant trick of Solovay-Kitaev in this version here would be, don't check how well you're approximating it, check how well you can invert or undo that target unitary in principle. And then you undo the whole thing and you get the unitary, right? So try to find a sequence of gates which is kind of destroying that unitary, destroying in the sense that it's destroying its effect, its impact, and it becomes the identity. Okay. So that's why maybe this picture with the Lie group. Okay. So let's have a look. What does it mean precisely? Okay. So that's what they are saying. So the point of this Solovay-Kitaev algorithm is giving increasingly better approximations to the unitary. So let's say we already have some approximation to the unitary, such that exactly what I was saying, it's an approximation at some level epsilon n minus 1, okay, at that previous step. It's an inductive iteration. So basically Solovay-Kitaev you should understand as an amplification algorithm, amplification of how well you're approximating the target unitary. Okay, so can we find an approximation to this attempt at inverting U, undoing U? Okay, and then if this new error of approximating that is small enough, you can just undo the whole thing and you get a better approximation to the target unitary. So we get a sequence of new gates, UN, such that the improvement is whatever gap of improvement we got here. And because of this, we will see that because of this delta here, can I select this? Because of this O of delta delta, as we were seeing, it's collapsing very fast. And then basically this is epsilon n is sort of epsilon n minus 1 squared, stuff like that. Okay. So the idea is that commutators of elements close to the identity approximate better than expected. So that's this kind of like rate of convergence that we were seeing, this very fast stuff. Okay, so we are not really explaining the proof here, but yeah. Okay. So yeah, so then at some point you need to put in the group commutator into play. And if I had more time today, then I would actually maybe go to that point in the paper. Maybe we still go there to see. And then that's more or less the proof idea. So we can use Wikipedia in this limited way. It's not explaining everything, but at least we maybe get some guidance where to go. So okay, so once we have this, we kind of understand the proof idea, and this is like this contractive, exponentially contractive flow, and basically let's have a look here. Can I find this? But okay, in terms of bridging tutorials, my point now, if I would be reading it on my own, would be to find a spot where you translate the approximations into the group commutator here. Okay, and why is this group commutator helping, and why do I get a better approximation, and so on. Okay, so basically they are saying we will be attempting to write U as a group commutator of some operations. Yeah, but you would need to read the full paper to understand the full notation. Okay, so yeah, and basically what you will find is what we will find is a lemma which is purely linear algebra. This is purely linear algebra. Some operations, those operations have this distance, then we have this distance delta, and here we have this O of delta 1 times delta 2. This is what this means. That's the idea. And that's this amplification. And we already saw before, this is something I was writing, that this amplification is a good thing. It's making it very quick. So basically this kind of angle contraction is happening here, and it's singled out as a mathematical result. And then you need to keep reading the paper to see how this comes into play. But we are on page number 8. And once you have this result, you kind of understand the full algorithm. So this is kind of here. Okay. So one thing that I want to say is basically at the initial step, you consider the basic approximation to U, and they explain it quite nicely. In order to implement this step of basic approximation to U, which is the initialization of the algorithm, we assume that there is processing that has been completed, which works for some epsilon approximation. And basically what they anticipate here is more or less a VQE, or variational algorithms. Variational quantum algorithms. Basically saying by brute force, consider all circuits out of my small gates and then some CNOTs and so on up to level D, or what now? Up to level L0, L0. Okay, so this is what we are saying here. Up to this level L0, I get some approximation U0. That's my basic approximation. Why is it better than considering L equals 1? Well, basically it becomes a circuit. It's not just like, okay, let me assume that my unitary rotation X tensor X is approximated by a C0. It's not. But maybe it's a better approximated by, I don't know, like some Rx rotation on top of it and so on. Yeah, so this kind of discussion is what we need. So for example, a CZ gate, if I want to approximate it, I would need some Z tensor Z plus Z tensor identity plus identity tensor Z, more or less like this. So if I wanted, for example, a ZZ rotation, I could put those things together and so on and so on. And basically doing this kind of in some tinkering way is included by brute force evaluating everything and then have a lookup routine. So basically lookup routine means I have 1 million different short circuits, and for the unitary that somebody is asking me to compile, in the first step, I will compare this unitary to all possible circuits at this depth L0. And I will return to you the best approximation in this short circuit. And then what happens is I go to step n equals 1. If n equals 1, then we go here. And basically, it's a recursive algorithm, and it's just going to improve that it's going to amplify this approximation. Okay.
So for the basic approximation, how do you get the lookup table?
For which approximation?
The basic case, the base case.
Yeah.
How do you get the lookup table for circuit length of
So
yeah.
Okay, so let's say I have 2 qubits. And let's say I have maybe Pauli X and Pauli Z rotations. I have some C0 or CZ, whatever. And so I can evaluate, for example, first I will only apply X, Z, and Y on all possible. So first I will do X identity. That's the first one. So my lookup table is X identity and nothing else. It could be also the identity on both. It could be Z here and Y here. So basically the first step would be maybe the T gate here, identity, single qubit rotations. Then I go to depth number 2. So maybe I will have X, Z, and C0. Then maybe I go to depth number 3, and maybe that's already it. So I will put the C0 here and the T gate here.
So this lookup table is gonna be enormous.
The lookup table will be all possible combinations of those gates with depth number 5, for example. Okay, so
yeah, so that's gonna be pretty big, right? I mean,
yeah.
if you have multiple qubits, that's gonna be huge.
Yeah.
Lookup table.
Yeah. So you can do it better. Basically, there are papers which are showing in SU4, so on 2 qubits, how to, in low depth, compile any unitary on 2 qubits. So if I have 2 qubits coming in and I have the unitary here, so this is SU4, it's actually not so complicated to get that unitary with phase rotations, different phase rotations and C0s. And the depth here is, if I'm not mistaken, around 10 for arbitrary rotations.
Yeah, I mean, I guess like for 2 qubit case, it's pretty manageable. But if you have like 100 qubits, then Like, how do you have a lookup table for that?
You don't. That's the point. That's where Solovay-Kitaev ends. You see?
So you just need a lookup table for 2-qubit case.
No, for 2-qubit case, this is called Sirac-Krauss decomposition, I believe, or papers related to that.
Mm-hmm.
Basically, for 2 qubits, it's possible to find more or less analytically this compiling sequence in terms of those C nodes and so on.
Yeah.
One interesting case would be, for example, if in superconducting qubits we have I swap, and I would like to have, for example, the swap gate. So I would have maybe X, Y, Z, Hadamard, and so on, all possible rotations plus I swap, how to get a C node, and so on. For this, you could use the Sirac-Krauss kind of theory and so on, or you could use Solovay-Kitaev, yeah. And I swap will be already quite close to maybe some CZ operation and so on. Maybe it won't be like too far, and then maybe you can initialize it, right? So as long as the approximation is not horrendously bad, if the difference U minus some sequence S0 is maybe smaller than 0.1, you can kickstart the algorithm. That's the point.
Okay. Maybe
So-
I'm being confused, but like, so this Solovay-Kitaev algorithm will allow you to extend this with a deeper circuit, right?
Yeah. But
like, in terms of number of qubits, like this is not gonna help. Is that right?
so lookup table will not work for more than a few qubits. Will be terrible, as you see from this endless list that I started writing, right?
Yeah.
For 2 qubits, we can do it more or less analytically. For 3 qubits, it's maybe already interesting to use Solovay-Kitaev and play some tricks.
Mm-hmm.
The thing is that if you have a good starting idea, then you're already quite good. So these days, we would replace this lookup table idea by basically saying you want some unitary on, let's say, 3 qubits. Then I will run maybe some VQE or something like this in Python. So I will use NumPy here. By brute force trying to find the phase assignments and the C nodes and how to correctly couple them and phi and C node and so on. So in the next round, I will couple those and then maybe I will couple those and so on. So I do it with a VQE without a lookup table, but case by case. So every time, if I had a lookup table, every time you give it to me, I could just search through it. Instead of searching through it, you give me this unitary and I try to find some stuff such that this minus my input unitary, that it's smaller than some threshold to initialize, for example, 0.1.
Sorry, I'm lost. Why are we thinking about the lookup tables? Like, isn't it exponentially fast anyway? Like, can we start from identity and just do the Solovay-Kitaev?
No, because unitary minus identity, it might be quite a big norm.
And for this to work, we need like initial approximation that is smaller than subthreshold. Or
I mean, you're amplifying, so anything strictly smaller than 1 will in principle work, right? Because I can put this to delta 0.
And it is exponential, right? So
it is exponential, but in the end, that's kind of, I think that's the kind of stuff that people were looking at in the last 15 years. So this is 2005, and now people would be really trying to crunch it and try to find the right stuff. So what Jongrak you're saying, and yeah, so maybe this lookup table you don't need or something like this. Maybe this is just like an offhand comment for them to say, this is not a problem. We are having all this discussion because maybe in practice it's not the best way to go forward, but definitely, how to put it, you want a good initialization in practice, even though this is exponentially good. Because for the physical gates, you're losing fidelity very quickly. That's the answer. So you don't want to start with from this identity.
Well, but when you compile it, you do it in a classical computer, and
Yeah.
So you're saying that like if you choose the wrong initial gate, then the gate depths would be larger.
Yeah, so maybe the optimization pathway, if you start from identity, let's say u minus identity is already smaller than 0.1, but maybe you can find a smart VQE sequence that will give you a starting point, which is 0.1 to some power alpha with some alpha larger than 1. And then you run Solovay-Kitaev from this, and you run Solovay-Kitaev from this, and maybe VQE found a better approximation than Solovay-Kitaev finds here, right?
Is that like obvious? Like if you start from a better initial guess, then you have like better compilation in terms of the circuit depths.
It's not obvious, but it can happen. The reason why is that we are optimizing over the unitary manifold, which is very non-convex. So this optimization can be very nonlinear. Why is it nonlinear? Is because there's so many Euler angles in general. So to be safe, if you're able to find a good starting point, try to use it. So for example, this would be just a random search, which is a short brute force search, okay? And then, for example, run Solovay-Kitaev algorithmically. Yeah, you probably don't lose much trying it out, and basically, as we discussed just now, this lookup table with depth L0 is maybe not so great. If you have a lookup table, it's basically doing the brute force search more or less without randomization. You check all possibilities, and then you find really the best starting point, and then you start amplifying. That's maybe this idea. Okay. So,
Okay.
yeah, but let's finish by saying that you really need to be able to make computations with you, because as we are looking at the algorithm, so this basic approximation, let's say we understood that we are kind of turning 0.1 into 0.01 and so on, so making the error smaller and smaller. And then we need to be setting stuff. So UN minus 1 is in the first step what we just got from, let's say, the VQA or lookup table or anything else. And then we are setting V and W using this GC decompose, group commutator decomposition of U times U dagger of our current approximation. So the key operation, key classical computation is given approximation approx from step n minus 1, which is UN minus 1, do computation, classical computation on U times UN minus 1 dagger, which should be approximately this identity. Okay, and this computation is GC decomposition. Okay, and that will answer the question by Kunhi, what happens if I have 100 qubits? If you want to be using Solovay-Kitaev on 100 qubits, you need to be able to do this group commutator decomposition on 100 qubits. Okay, so let's look at the group commutator decomposition. Can we find this? GC approx. Sorry, I'm getting tired. Maybe too many scribbles. Once we find this group commutator decomposition, we are done. GC decomposition. Decompose. Okay, so decompose delta as a group commutator. So basically delta is our approximate undoing of our target unitary. So basically, to be able to find this compilation sequence, the compilation sequence is essentially UN. To find that, we need to be able to manipulate an operator delta. So let's say doing it in NumPy. In NumPy, I can do it for 12 qubits. I cannot do it for 100 qubits. That's the point. So what we will need to be able to do is to find a decomposition of delta as this group commutator operation. Okay. And basically, once we find W and V, then we return this. We return it here in this step as V and W, and using V and W, we will compute. We will compute UN. Okay, so basically, once you have V, you want to again recursively compile this V. Okay, and then what we will do is that UN will be the compiled V and W group commutator. Okay, so basically it will be an approximation to the delta. Okay, let me write this and then we are more or less done. Okay, so Vn minus 1 is approximation to V, and Wn minus 1 is an approximation to W. Okay, and once we have this, then we had that delta is this. So now we have delta V W V dagger W dagger. This is approximately Vn minus 1 Wn minus 1 Vn minus 1 dagger Wn minus 1 dagger. And when we have this, it means that we are approximating it. So we have some delta tilde. And basically our new updated approximation is delta tilde UN. If the approximation is perfect, then this this delta is UN n minus 1, sorry, here, dagger, which would mean that this is approximately UN minus 1 dagger UN minus 1, which is U. Okay, that's why UN is approximating U a bit better. Okay, so there's many scribbles now in the pages. Sorry about this. I will go back to the clean paper. So that's our algorithm. So what we need to know is we will be amplifying an initial approximation. So we need to be set on the way well. How to do it from the beginning? Since 15 years, we say like you just choose your approach, you choose. Once we have this, the algorithm will be recursive. So it will be asking us to compile some few step approximation to U, and then use a decomposition from linear algebra. Okay, so later I will just scroll down to say that this exists. So this is a procedure which is similar to matrix diagonalization, and to run diagonalization, you multiply matrices. Okay, so how well this compiling scheme works for many qubits is the question, how well can you work with those operations? But if you can work with them well, you don't need the quantum computer. Okay, so this is the step. Essentially, this decomposition is the step when you hit the limitation of using this compiling. And then later you need to be more analytical and you need to construct circuits as a circuitry and not a compilation scheme per se. So you do the compiling by writing a program, okay? Not just by brute force finding the algorithm. Okay, so we are almost done. The only thing that I need to find now is to find where we have this decomposition showing that it exists, but I think I was already showing it. It was some citation from Horn, I think. So if I have any operation, then I can find that this is the commutator. And then more or less, they will explain that basically you can exponentiate them together and that will give you the operation that you need. Yeah, so this is more or less the group commutator bound expressed a little bit differently than I was showing it, but basically I was maybe improving the constant C from away from this to the commutator of FNG. Okay, so that's the improvement in the previous sessions. Okay, but basically you constructively decomposed our delta into the commutator of those two. So no, sorry, we will have the delta and then we will take the logarithm of the delta that will give us some h. And then we will decompose the logarithm of the delta into a commutator, and we will do, then basically delta is the exponential of the commutator, so we will approximate that commutator using the group commutator. That's why the group commutator comes in, and then you're done. Okay, so I finish here. That's basically Solovay-Kitaev algorithm. A lot of limitations, but also a lot of power, a lot of research done, quite beautiful stuff. It's really great that there are those advances, and yeah, the power of it is that it really gives you a deterministic sequence. The power of it is that it's able to improve for you many things. The limitation of it is that you need to be able to find those decompositions, and the decompositions I didn't discuss. It's something that you would implement numerically. Okay, so that's all the ingredients. Okay, I think I finished here. Yeah?